Hey everyone, my name is Courtney and I'm here with Alana, and this is our Engineering 305 Presentation 7 video. So in this video we're going to be talking about reliability and survival in JMP, and the first method we're looking at is distribution fitting of life distributions. So the JMP data set we'll be using is FAN, and we're looking to explore and find the best distribution and graphically depict failures for this time to event data. The tools that we'll be using are the life distribution tool in JMP to get our results, and as I'll show you in the example, but some of the results that we found is that the log normal fit was the best distribution to model the data, and that the quantile profiler said that the average estimate of the engine fan life was 25,000 hours, basically. Okay, so now we're going to go into JMP for this first demonstration. So here's our fan data, and to do the life distribution, you go to Analyze, Reliability and Survival, then Life Distribution. To set it up, we're going to put our time to event, which is time, and if you have any censored data, you'd put that in the censor field. And we're not going to mess with any of these today, but you can change these based on your data. So we'll click OK. And here we have a bunch of different data that we can look at. So you have an event plot, which graphically depicts failures denoted by X's, and censored events, which are denoted by the triangles. So for this event plot in particular, again, these X's are just the failures, but the ones that are, these are considered right censored values, which means that the unit did not fail during the study time, which is the solid line, but it will fail in the future. You just don't know when. You also have the compare distribution panels, which allows you to compare the fit of various distributions. The goal is to get the data points kind of like in a straight line and to fit. So if we did log normal, not too bad of a fit, and then you can also change the scaling to try to make it more accurate. As you can see, that made it much more accurate. These are the shaded area is considered your confidence bands, and you can also get this distribution profiler that comes up depending on which distributions you add. It'll add to the profiler for you. And you get some statistics down here. You can see your AIC and your BIC for comparisons. And an important one to look at is your profilers down here. You get 4 different types of ones. So the distribution profiler shows cumulative failure probability as a function of time. Your quantile profiler shows failure time as a function of cumulative probability. And then your hazard shows the hazard rate as a function of time. And finally, the density profiler shows the density for the distribution. But as I mentioned in the slide, looking at this quantile profiler, you can see that there's a 0.5 or 5% probability that the engine fans will fail at this hour, which is something important probably to look at.
So now I'll be discussing the fit life by X. It's really similar to the fit Y by X in JMP, but instead of using Y, we're specifically looking at something for a time interval. So the main thing that we want to accomplish with this type of testing is to model a relationship between the time to an event and the factor of interest. So in JMP, we're going to be using the vault data, and the factor of interest that we're looking at is going to be temperature. And so some results that we found were that the log normal fit the best, same with the previous data type that we used, and the qualifier showed that it was at 50% probability the default will be failing at a temperature of 45. So now moving into JMP, again we're using the default data, and we're going to click on Analyze, Reliability and Survival, Fit Life by X. And we're going to be putting hours into this Y column, and then temperature, as we said, is the factor of interest in the X, and sensor in sensor. Normally, having the number 1 means that we censored data. And right here, if you click on this red arrow, you can say that 0 means that we censored data. This would normally be the case if we had a factor called cost, which cost is literally the opposite of censor. So we would just change that and click 0. But here we're using censor, so we're just going to leave it as 1. And we're just going to unclick this nested model test. So I'm going to click OK. And then this pops up, a scatter plot of the data points and the different things that we can look at, so the different comparisons. So going back to the scatter plot, I want to click on show density curves, and it shows where majority of the data is. Like, it just gives you a distribution of where the data points concentrate at. And we can click on the different tests. So remember I said that log normal was the best. We're going to compare it with the log logistic as well. And you can see they're very, very close. So going down a little further, we can see the statistics of the entire thing. So right here, we can see the AIC, and it's giving us a value of 577.156. And I'll go down a little further to look at the log logistic results, and that's giving us an AIC of 577.165. And it is very, very close, but the one with the lowest value is the one from the log normal, which shows us that this is the best model that we have. So going back up here, we're going to go to quantile. And in the quantile, we're looking at log normal again, since we've determined that that was the best. And we can see that at a probability of 0.5, which is 50%, there it's going to fail at a temperature of 45. So thank you for watching our video.